Hi, it's Paul here with a little script designed to illustrate some of the ideas of general topology. Don't worry much about how the R code does what it does. Just concentrate on the diagrams that it draws. If you want to run this yourself, you'll have to install a special package called Plottrix that has a function for drawing circles. You only have to do this once. Since I've done it on the computer where I'm making this recording, I've commented the line out, but I've left it there just in case you want to run the script yourself, and then you call the library function and you have access to the function draw.circle. So first I'm going to draw the website diagram that appears in a number of places in the notes. Leave plenty of margins, draw a blank plot with appropriate limits on x and y, and specify the x-coordinate and the y-coordinate for the centers of the 6 circles that will represent 6 pages on a website. So I draw those lovely 6 circles, and now I set up links between these by creating a matrix. Each column of the matrix shows the links going out of one page. So if you look at the first 6 entries of this 6 by 6 matrix, 0, 0, 1, 0, 0, 0, that says that from page 1 you can follow a link to get to page 3. And it's easy enough to draw all these by running through the entire matrix and drawing arrows to represent the links. The links that I drew in red are two-way links, which means that from page 4 you can get to page 5. From page 5 you can get back to page 4. And the same is true of 1 and 3. Now what's remarkable about this is that you can make a definition of open set that's consistent with all the axioms of general topology. And our definition of an open set of pages is you can't reach anything in that set from another link that is coming in from outside the set. So an obvious example of an open set is 2. From 2 you can get to page 1 or page 3, but if you're on any of the other 5 pages of the site, there's no link that takes you to page 2. That makes it an open set. Similarly, 4, 5 form an open set. You can get back and forth between 4 and 5, but there's no link from outside. And clearly 1, 2, 3, and 4, 5, 6 are not connected with one another, so they're 2 open sets. One of the axioms of topology says that the union of open sets is always another open set. And sure enough, if I take the union of 2 with 4, 5, you can't get into that union from outside either. The first axiom of topology says the empty set has to be on your list of open sets, and so does the universal set X, the one that in this case consists of all 6 pages on the site. A closed set is defined to be the complement of an open set, and so for example, since 2 is an open set, its complement 1, 3, 4, 5, 6 is a closed set. The complement of 4, 5 is 1, 2, 3, 6. The complement of 1, 2, 3 is 4, 5, 6, which is a closed set. You say, hey, I thought that 4, 5, 6 was an open set. No problem. It's entirely reasonable for a set to be both open and closed, and there are also plenty of sets that are neither open nor closed. If I take the intersection of 2 closed sets, I get another closed set. So if I look at the elements that my first 2 closed sets have in common, that's 1, 3, and 6. That's a closed set also. And so is page 6 all by itself because it's the intersection of 1, 2, 3, 6 with 4, 5, 6. The empty set and the universal set X, being complements of open sets, are also closed. Now, here's a way of thinking of closed sets that is more consistent with the idea that if you have a closed set, the limit of a sequence has to be in the set. start on page 4. You can follow the red link to get to page 5. You can follow the blue link to get to page 6, and then you can't get any further. And what you've discovered is the closed set 4, 5, 6. More generally, if you start on any page and just keep following outgoing links till you can't reach any more pages, you will have constructed a closed set. That's kind of like following a sequence of real numbers and getting a limit that wasn't in that set. The interior of a set is defined to be the largest open set contained in that set. What do you mean largest? I mean the union of all the open sets inside it. The closure of a set is defined to be the smallest closed set that contains it, and the boundary is the difference, that is, the pages that are in the closure without being in the interior. These same definitions work for intervals and other sets of R, and they also work in Rn, but I want to make the point that these are general definitions valid for point set topology completely in general. Let's generate a random subpage. 2, 3, and 5 is a set, and we'll try to answer the question, what's the interior? The interior is 2, because that's the only subset of 2, 3, 5 that's an open set. If I look for the closure of that set, well, I can follow links out of 2 and get to 1 and 3. I can follow links out of 5 and get to 6 and also to 4. So I think the closure of this set is the entire web page. If you want to play around with more of these, you can draw the 6 pages, but then link them together randomly. I've set up 2 two-way links. Then for the 2 pages that weren't included in those, I set up a one-way link. And I also generated some random links. Any entry in the matrix started with an 8% probability of being a 1. Since no page can link to itself, I'd better set all those entries to 0. And here is the resulting matrix. This tells us, for example, that following links out of page 1, you can reach pages 5 and 6. Following a link out of 2, you can reach 1, and so on. You can draw this, and you get a different topology that you're free to analyze on your own. Look for closed sets. Look for open sets. Look at intersections and unions of open sets that are also, therefore, open. Same thing for closed sets. And you can even find the interior closure and boundary of a randomly generated set of your choice. But I'll leave that for you to do on your own.